Messed up my recording. I guess I'm gonna have two videos. Um, anyway, is there any more questions on these bound questions? All right. I guess let's any other questions? I'm gonna go out. I'm gonna actually back out of 9.4 here.
Can you do 9-3, number 17?
Sure, let's take a look at that one. All right, let me share the screen. Use calculus. Here we are. To determine the exact y-coordinate of the highest points in the curve y equals sine 2 theta. I guess we want the max y value. So, all right, as usual, I'm going to go to Desmos. I have no idea what this thing looks like. Give me a second here. So I'll type in r equals sine 2 theta. It's a four-leaf clover. And it looks like it wants this point up here at the top. Okay. And all right, so again, I'm kind of thinking out the problem here. We want to find where the slope of the tangent line would be horizontal. All right, that looks like what we want to do. All right, so I'm going to stop the share. Actually, you know what? Let me copy that real quick. I just need one of these little clover leaves. That's good enough. All right. So what we're going to do here is we need to kind of get this thing back in X and Y nomenclature because we're looking at this when we talk about a horizontal tangent, we're actually kind of looking at this in the X and Y Cartesian way. So I take the sine 2 theta and I multiply that by cos theta, and then I take the sine 2 theta for y, multiply that by the sine theta. And this is just using that basic um, conversion. X is r cos theta, y is r sine theta. You definitely want to know that for Calc 3, by the way. So there you go. And so what I want is dy dx equal to 0. And that's the same thing now. In this realm, we can do dy d theta over dx d theta. And so it's really the same thing as asking when dy d theta is 0. So really, the action's occurring right here. And so I'm going to need to differentiate that traditionally. So dy d theta product rule. So first sine 2 theta, derivative second, which is cos theta, plus the second, which is sine theta, times derivative first, which is 2 cos 2 theta. And unfortunately, we've got kind of apples and oranges here because I want to set it to 0. And but it's kind of tricky when you've got both 2 thetas and just regular thetas. So we're going to have to replace these. Uh, this is where you bring in identities. The sine of 2 theta is 2 sine theta cos theta. And then, of course, this cos theta. And the cosine of 2 theta is actually a couple of them. And I'm thinking, well, let me come over here. Cos 2 theta actually has a couple of cos squared theta minus sine squared theta. And I really don't want to be getting into powers if I can avoid it. What if we do, because I got a sine here. So how about 1 minus 2 sine squared theta? I can't forget that 2, so I got to keep them out in front. Let me pause here. Does it make sense what I'm doing here?
Sorta.
Okay. Um, yeah, I'm just simply trying to find this horizontal tangent line, which means the slope is zero. And it's kind of implied that a zero slope is horizontal. That's Cartesian, so I have to convert back to x and y. And finding when the slope is zero is the same as finding when dy d theta is zero. And this is where we are. This just becomes kind of you really got to beat this with a stick. This thing is now that I think about it, I'm wondering. Well, let me see over here. I actually have 2 sine theta cos squared theta. Actually, you know what? I think what I'm going to do, because I could probably get away with using cos 2 theta is also, because I like, it's also to do 2 cos squared theta minus 1. No, that's not correct. Hold on. So again, I remember this one, cos squared minus sine squared. That's the cos of 2 theta. If I replace sine with negative 1, sorry, 1 minus cosine squared, actually, I had that right. It was 2 cosine squared minus 1. I'm going to have, then distribute the sine through, I'm going to have, looks like I'm going to have 4 cosine squared theta sine theta minus 2 sine theta. So I'm distributing 2 sine theta through this thing right here. And that does allow me to combine a couple of terms here. All right, this thing is starting to take shape. And now I want to set it to 0. And it looks to me like I can factor out a sine theta. In fact, I can factor out 2 of them. And that leaves me with 3 cosine squared theta minus 1 equals 0. From here, I get a couple of values. I get theta equals 0, pi over 2. I'm sorry, I'm just pi, my bad. Just pi, 2 pi, etc. From here, it looks like we're going to get some interesting values. We're going to get cos squared theta if e equals 0, bring the 1 over, divide by 3 is 1/3. So if I take square root of that, I get rad 1 over 3, which is rad 3 over 3. And that's not a usual, that's okay. That one is just going to have to work out using a calculator. So theta would be inverse cosine of that. Let me do that real quick. So it'd be inverse cosine square root 3 over 3. And I get 0.955. I'll just take it one more. That's the theta value. You take that theta value and take it all the way back up to here to get your y value. Yikes. So y equals sine of 2 of this value times sine of that value. So there you go. Oops, sorry about that. I wonder if I did that right. That seems right. Um, I'm looking at the key. It looks, yeah, it looks all right. They do it slightly differently. It looks to me, I don't think I made any algebra mistakes. I would, well, let's try something here. I'm going to go back to Desmos. I hope I did this right. So give me a moment here. I'm going to go to my Desmos screen. Let me erase what I had there. The function was r equals sine to theta. And we discovered that when theta is 0.9553, aha, I think we did it right because that puts us right there at the high point of that pedal because that's the highest that y gets. So I'm feeling pretty comfortable about that. Oh, yeah, there's a lot of opportunities to make mistakes on these. I agree with you there. All right, we get sheet. 9.2, number 8. Share the screen. Which of the following integrals represents the length of the parametric curve x equals ln t? Let me copy this down. Y is rad t plus 1 and 1 to 5. I'll come back to this here in a bit. Let's just see what we got here. Generally, the arc length is an integral of the radical where you take the derivative. So this would be dx dt squared plus dy dt squared. So the derivative of x is ln t. I'm sorry, the derivative of ln t is 1 over t. I'm going to square it. So this is just Pythagoras' identity here. And right here, I'm going to have 1 over 2 rad t plus 1 dt. That should be the answer. What do they do? Um, Give me a second here. It looks like they're simplifying. Yeah, this, hold on a second. So I'm going to share the screen again. Well, clearly what I wrote down doesn't look anything like what you see here. It looks like what they did is they simplified some more. So let's do that. I'm going to unshare the screen. This is correct. If I just need to pop on the bounds, 1 to 5. Actually, no, that's not correct. Let's see, it's a T. Yeah, it's correct, 1 to 5. Okay, my bad. I was thinking of something else. Let's see what we got going on here. I'm just going to play with the square root portion for a little bit. It's going to be 1 over t squared. And then when I square this thing, I get 1 over 4 t plus 1 because it squares away the radical. And then if I bring together a common denominator, you're going to get 4t plus 1 here and then plus a t squared here. And it's really not simplifying very much. I have no idea if that's one of the options. Let's see. does not look like it is. Um, oh, I made a mistake right here. That's a 4. Oh, okay. On the top, this actually factors. This is going to be t plus 2 quantity squared. And so the radical of the square just leaves a t plus 2 without a radical on top. And then the bottom, we can take out the 4t squared, and that's just 2t, but then leave the t plus 1 in a radical. That looks like it's option F on my screen. Now, I will say this. This to me is kind of you don't need to do all this, let's just say, because this right here is good enough. All right. More than likely, especially when you're doing arc length, you're going to get an integrand that just doesn't integrate. This thing is going to be nasty. I'm not sure it can be done. It can be done numerically, but I don't think it can be done analytically. If you take Math 267, we talk about arc length quite a bit because it pops up in a lot of our discussions. And I always tell the students in that class, just make sure you set it up correctly. Don't worry about appearances. Just make sure it's set up correctly. So for example, this kind of question, um, if it just simply asks you what is the arc length, instead of picking the right integral, it just wanted to know the arc length, get it set up right. So I would leave it in this form. And then I would let Desmos well, since you have to use Desmos, I would actually type this function into Desmos just the way it is. Um, it looks rough, but Desmos will handle it. That's my suggestion. So if you get a question where it wants the actual arc length, so if I scroll down, let me just share the screen real quick. So like number 9, for example, this one, yeah, you could set it up easily. The xdt is 12t, the ydt is 12t squared. When you square those, you get 12t quantity squared plus 12t squared quantity squared all underneath the radical. I ain't gonna mess with that, but trying to work it out analytically will be very difficult, if not impossible. But once you get it set up, then just feed it into a calculator or on Desmos and let it do the actual calculation. Because trying to work out these radicals is nasty. All right. So it looks like on a lot of these, especially if it's the arc length, if all it wants is the length, it doesn't care what form you give it in. If you set it up right, that's 95% of the battle. And you can let the calculator or Desmos do the actual calculation. Did y'all get my message about extending the day 1 day?
Yes.
Oh, yes.
Okay, so it still starts on the 30th on Thursday at 4 Mountain Time. Um, I teach at ASU's main campus those evenings, so that's why I'm not really available. But then Friday, I'm going to be doing more furniture moving. It should be the last day of that. So that's why I'm not available. So we closed down a house a couple weeks ago, and I've been moving furniture the last 3 weekends. So I'm still doing that at age almost 60. Um, so I'm extending it 1 day, but that means I will get grades calculated by definitely that Sunday morning. I want to get these things submitted ASAP. I'm sure you guys do too. So I will not delay on that. Well, I'll tell you what. Again, I appreciate you guys working hard this semester. You just got one more big hurdle ahead of you. Um, if you think of any questions, put them onto ed discussions. We'll tackle them there. Otherwise, best of luck to you all. Okay. So I'm going to go ahead and power down if there are no further questions. I appreciate that. And you guys, do as best you can and enjoy whatever break you have that comes after this class. So 5, 4, 3.